water. What's the water acting as? It's an acid. So this is where you have an acid-base reaction that doesn't fit the Arrhenius definition. The Arrhenius definition, which was developed in the late 1800s, said nothing about protons being donated and accepted. Why did the Arrhenius definition, which was developed in the 1800s, have that part of it?
Didn't exist.
They didn't know protons existed. They said, wow, we got hydrogen. They didn't know anything about protons. Okay? Now, this is the classic situation. This is acting as a base, but there's no hydroxide in it. This is why they had to come up with a new definition of acid-base reactions, because you were generating hydroxide, you were making something, but this didn't have an OH in it. That's where they had to come up with a new definition of it. Okay? All right.
How do you do 6?
Huh?
How do you do 6? Oh, what's it asking?
Well, let me ask you this.
Oh, is it mean the numbers from 4?
Yeah.
Okay.
Yeah, it's the same numbers from, otherwise I have to give you new numbers.
That's right.
Yeah, do not make, yeah. 4 and 6 are the exact same numeric answer. Okay, number 6 is the easiest question I will ever ask you in this class. Do not make it complicated. Okay, now here's what I want you to see going into this backside. So the acetate is acting as a base. It's reacting with water. You're going to reform the acid and the hydroxide. On 13, write the dissociation equation for acetic acid. If you want to throw in water, you can, but you can just write it as HC2H3O2, turning into the hydronium ions and the anions. If you want to be a purer to the idea of what's actually happening, you could throw in the water molecules, because that's technically what happens. And you're generating hydronium ions and the anions. Okay? Technically, that's what's happening. That's the more pure way of doing it. So, what you should see on 16, when you multiply the Ka times the Kb, you should end up with your hydronium ion concentration times your hydroxide ion concentration, which does not equal water. That's why that's up there on the things that annoy me. Okay, now that makes sense. Okay, on the things that annoy me. Does it equal the auto-ionization constant of water? Yes. Okay, 1.0 times 10 to the negative 14. That's true. Okay, doesn't equal water. Oh, Ka times Kb equals water. Shut up. No, horrible. So your answer to 18 should be something times 10 to the negative 10th. Okay? Pretty small number. Your pH on number 19 would make an GPA.
So like between 2 and 3.
That, by my definition, would be an GPA. Between 2 and 3. Okay? Now, let's talk about number 20, because this is what I'm going to get into, what's called buffered solution. So I was nice. I even gave you the reaction. Okay? Going to yield hydronium ions and the anions. Okay? Now, here's what's different. Up to this point, and you have a 0.5 molar solution of the acid. Notice this is not a stoichiometric calculation. We are not adding hydroxides. We are not neutralizing anything. No moles are involved in the creation of this problem. Okay? Nothing is getting consumed. Mother Nature is just trying to get to a point of equilibrium. That's all Mother Nature is trying to do. Mother Nature is just trying to chill out. Now, up to this point, what did you assume the hydronium ions and the anion concentrations equal? 0. You assume that those are starting off at 0. Okay? That's it. Because that was it. It was 0. But here's the difference. This is the cool part. This is not starting off at 0. It's starting off at 0.75. Okay? So we're not starting at 0. So that initial line on 20 needs to be 0.50 and 0.75. Now, it's the same process. You're going to go minus x, plus x, plus x. So the next line is the exact same. Same process, just like you've done before. This is not anything new. This is 0.5. Technically, we're subtracting x, but it doesn't matter. This becomes x. This becomes 0.75. Now, here's where you have to go to how you calculate Ka. So your Ka is going to equal your hydronium ion concentration, which is x, times your anion concentration, which is 0.75, divided by 0.50. Okay? Now, listen to me. Prior to this point, what did these two values both equal? Same thing, you just called it x squared, right? Multiplied by 0.5, Ka times 0.5, you took the square root of that, boom, there you go. This is not that, okay? Because this is what we call a buffered solution. We're starting with an anion solution that isn't 0, it's 0.75. Now, here's the heart and soul of this. Mother Nature still wants the exact same Ka value, okay? This is important that you understand this. Mother Nature wants the same Ka value because that's when Mother Nature's in equilibrium. So Mother Nature still wants that 1.8 times 10 to the negative fifth. I think that's the Ka of acetic acid. So here's the difference, okay? You have to understand this difference. Whatever Mother Nature does, she's going to end up with that Ka value. Doesn't matter. Mother Nature wants that Ka value. Now, here's the difference. If it's a non-buffered solution, those are both x and x, and that's 0.5. Mother Nature goes, fine, hey, we're going to do this in a 1-to-1 ratio because that's how we roll. We're going to roll in a 1-to-1 ratio. This is not what's happening here. Okay? Bad. Now, but what is true is that Mother Nature wants the same Ka value because Mother Nature still wants to be in equilibrium. Mother Nature still wants to be mathematically equivalent to that same Ka value. Mother Nature's going to do whatever Mother Nature has to do to make this happen. Now, here's the difference. By creating such a big concentration of your anions, now I don't need as many to get the same Ka value. So with the smaller concentration of my hydronium ion concentration, what happens to your pH? It increases. So your pH on number 20 should be around 5. Okay? So when you get to 21, explain the differences and the similarities. Okay? Notice that you need to address both. What's the same? And yes, I'm going to use the D word. And what's different?
Whoa.
Hey, I prefaced it. I said,
I know my point.
no, absolutely not.
Holy
Absolutely not. So here's the sequence that I want this handed in. I don't need the initial set of instructions. I don't care. I know what the instructions are. So what I want is the magenta page 1. Then I want yellow sheet. Okay. Then I want the 3 graphs in the sequence trial 1, trial 2, trial 3. And again, make sure that I have the 3 lines clearly visible on the 3 graphs. Okay? So, magenta, yellow, 3 graphs.
If we have any like extra data, do you want to put it like that behind?
Yeah. If you have any extra data, put that behind the yellow sheet.
So if we show our calculations for standard deviation 1,
Yeah, that's
Can I use the bathroom?
all right.
or